I left my book in Castro, so I couldn't do anything. So I have to pick it up today
Yeah, we
after
have,
school.
she has one, she's just looking for her homework.
Number 16.
Okay, the question is this, they give you a whole list of numbers, various fractions, percents, and decimals and whatnot. And they say, which of the values can represent the probability of an event? Now, what they're saying is, some of these numbers will probably be out of the range of probability. Probability just goes between 0 and 1. Okay? So you know that a probability has to be less than or equal to 1, greater than or equal to 0. Now, how you express that can vary tremendously. It can be decimal, can be a fraction, can be a percent, and so forth. So you run through that list, there's 8 of them there, just to check to see if they fit. 1.62, no, that's too big. Minus 7/5. Well, that would be a negative number, first of all. And we've never talked about negative probabilities. There isn't such a thing. And 7/5 also is bigger than 1. So, no, 7/5 minus 7/5 is not going to work. 0, yes, 0 could be a probability. 1 can be a probability. 200%. Now, 200%, if you talked about that in terms of regular old numbers, what would 200% look like? Well, we drop the percent sign, divide by 100, huh? That's our instructions to get into something we can work with. And that would turn out to be 2. Well, 2 is outside this range too, so that's no good. 200% won't work. 4.5, outside the range. Now, how about 4.5%? Okay. Once again, get rid of the percent sign, but then you have to divide by 100. Okay. Now, what is that? 4.5, well, let's just sort of estimate it. 4 over 100, that would be a very small number, huh? But would it be between 0 and 1? Oh. It would be, yeah. It's got a numerator less than a denominator, so therefore it's a fraction. It does lie in this range of 0 to 1. So strangely enough, 4.5% is a probability. That can be a probability. 0.87, likewise, 0.87 lies in this range too. That's 87 hundredths, and that is a number between 0 and 1, so that's okay. It's what's called a proper fraction. Numerator is less than denominator. Yes, it lies in that range. So the ones that do work are C, D, G, and H. C, D, G, and H. And the others do not. Any other questions?
Number 19.
Number 1?
Number 19.
Okay.
Number 19.
19. If a single die is rolled, what is the probability that it will come up with an even number? Okay, now we have to go back to the basic definition. Huh? Probability is the number of elements in an event divided by the number of elements in the sample space. Now, a single die, what would its sample space look like? Well, curly brackets to write down space, that's called set theory notation. And you just list what could come up if you roll a single die. You get maybe get a 1, get a 1 little dot. So you get 2 or 3 or 4 or 5 or 6. So that's the actual sample space. That's all possibilities of rolling a die, a single die. Okay? Okay, now when you look at that, you say, well, what I'm interested in is the number of elements in rolling an even number. Well, how many times could that happen? 2, 4, 6. Those are the even ones. So there's 3 in the number of elements in the event, and there's 6 in the number of elements in the sample space. So it gives you a 1/2, which you could write as 0.5. Or if you wish, you can multiply that by 100 and get 50%. Any one of these things is a perfectly good way of expressing the probability of getting an even number. Again, please keep in mind that this has to do with many, many tries. You know, you're talking about large numbers of rolling a die. And when you get up to maybe 40, 50, 60 times, then you start getting 50% even. It's not going to be a small number. Anything else?
The one with the 2 dots.
The 2 dot. And then dice.
29.
You find which
No,
one
that's
you're
the-
interested in?
that's the base
Number
card
11.
one.
Number 11, yeah, okay. Okay, number 11. It says 2 dice are thrown and the sum of the top sides is observed. Determine the sample space. Okay, now top sides, of course, you're looking down on it. And the question is, what numbers can you get when this happens? Well, if you're throwing 2 dice, of course, they're identical. So you could get, let's start with a very simple combination. You get 1 dot on one, 1 dot on the other. Huh? That could happen, okay? That would be the number 2, because they add up to 2. 1 plus 1 is 2. And then what could you get? Well, 2 dots on one, 2 dots on the other. Huh? If you get 4, could you get a 3? Yeah, you get 2 on one, 1 on the other. You could get a 3. And how about a 5? 4 on one, 1 on the other. Yeah, you could. In fact, you could get all these numbers all the way up to how much?
12.
Because this would be 6 dots on one and 6 dots on the other. That's as high as you could go, right? Okay. So this is the class on Las Vegas.
What about all the combinations though?
That is all the combinations. Strangely enough, that is all. You know. The only thing you can't get is a 1. Not with 2 dice, that's right. Okay, any others? There's one over here. 29, do I?
Oh, yeah, 29, please.
Okay. Okay, in a deck of cards, there are 12 face cards, which means, you know, kings and queens and stuff like that, and 40 cards with numbers. What is the probability of selecting a face card from a deck? Well, again, we go back to our basic definition. It's going to be the ratio of 2 numbers. It's a fraction. And if it is a proper fraction, the numerator will always be less than the denominator, unless you have a probability of 1 when they're equal. Okay, so the number of elements in the event that we're interested in, what event are we interested in? Drawing a face card. Well, the number of possible elements in that, they tell us, is 12. So the numerator has to be 12. And the sample space is not only the face cards, but the number cards. And the number cards are 40. So you have to add those 2 together to get 52 for the total sample space. So it's 12 over 52, and you can reduce that if you want to and write it as a decimal, anything you want. It turns out in reduced form, it's 3/13, and then you divide it if you want a decimal, convert it to a percent or whatever. But that is the probability, 3/13. Okay, any others?
37? 37?
37. Mr. Gutierrez has noted the times in which his students entered his classroom and constructed the following. About 10 minutes early, he gets 1 student. I don't.
Yes, you did.
No, I don't. About 5 minutes early, 6 students, on time, 11, about 5 minutes late, 7, about 10 minutes late, 3, about 15 minutes late. Okay. All right, what is the probability that a student will be early to class? Okay, so in order to do this one, we have to find out how many students are in the sample space, huh? And that gives you a column over there which tells you the number of students that were checked. 1 plus 6 is 7, and 7 and 8, 11 is 18, and 7 is 25, and 3 is 28, and 1 is 29, huh? So sample space, 29. The number of elements in the sample space. Okay, now when we're talking about early to class, there's only 2 categories here, 10 minutes early, 5 minutes early, and that contains an element space, so to speak. The number of elements in that event is 7. So you take the 7 divided by 29, and that would be the fraction of students that will be early to class.
Isn't it 30?
I think it's 29. Yeah. What is the probability that a student will be late to class? Well, there's 3 categories there. 5 minutes late, 10, 15, and 7, 3 is 10, and 1 is 11. So late to class is 11 29s. And arrive on time or early, that would be on time or 5 minutes early or 10 minutes early. That's 11 and 6 is 17, 1 is 18, that would be 18 29s. There it is, it's fractions, you could write it any other way you want to. But they ask about a percent on that last one, so let's convert that to a percent. If you divide that out, you have 0.62, multiplying by 100, 62% will be on time or early. And it's amazing, you know, I mean, this has to do with large numbers, but these figures actually work pretty well for this class.
You were reducing at 18 and 29?
You would,
You reduced?
where did the 18 come from? Is that what you're asking?
On number 29, I'm trying to figure out how to reduce the 12 and 63 to get 3 and 13. So,
I reduced the fraction.
how do you reduce?
Yeah, this is not in lowest form, because you divide the top by 2, and actually the largest number you can divide by is 4.
The largest?
So you divide 4 into 12 is 3, 4 into that is 13. So it becomes a reduced fraction there. And once again, even in probability, you don't write a fraction and leave it unreduced. You know, you have to reduce all fractions. People won't understand what you're doing. Anything else?
Oh, yeah, number 41?
41? If the probability of having twins is 1.2%, what is the probability of not having twins? Okay, this has to do with complementary probabilities. The probability of something occurring plus the probability of it not occurring has to be added up to 1. So having, let's just call it T for having twins plus not having twins, and then T has to add up to 1. Okay? All right, well, they give us the probability of having twins. They tell us it's 1.2%. 1.2%. Now notice they've switched over to percents here. That's the probability of twins. We don't know the probability of not having twins, so we have to find that. Now, in order to switch over to percents, we'd have to switch that 1 also. And that would require multiplying by 100 and put a percent sign on it, so that would be 100%. So if you subtract 1.2% from this side and subtract 1.2% from this side, you're going to get 0 there. The probability of not having twins will be 98.8%.
I got it. If you're trying to figure out the probability of something that's not a percent, let's say it's a number, how would you do it, though?
Well, then you just keep that as a 1.
Okay.
Yeah, I'm just converting it to 100% because they do give us percents. But if they don't give you a percent, if you just give me a number, a decimal, let's say, we look as a 1. Yeah. Any others? 27? Anyone else have a request? No? Okay. Probability that Julia will ask is very high.
Yeah.
Okay.
That was a weird one.
All right. What is the probability of an impossible event? Okay, just think of the definition of probability. That gives you a hint. It's the number of elements in the event divided by the number of elements in the sample space. Okay. Well, the number of elements in an event that is impossible is how many? Zero. To the top of zero. So it doesn't matter how many numbers are in the sample space. You've got zero divided by something. Who cares what it is? And that's always zero. So an impossible event, zero probability. I'm sorry?
What is that, underneath the zero?
It's nothing. Forget it.
That was his, who cares?
No.
All right, let's go on to chapter 10. Well, we're headed toward the last time around the track here. And what we've got to do now is prepare ourselves for algebra. And that preparation involves expanding our number system. So what we're going to do is take a look at the number system the way we have it, and then attach an add-on, so to speak. Drawing the number system as what's called a real line is very common. And it looks like this. The line, of course, has arrowheads on either side, meaning that they go to infinity. What we've been doing is this. We've used what's called zero and what's called integers. 1, 2, and so forth. And we've also used fractions. And fractions also go in there. You can picture fractions on a number line. For example, 1/2 would be about 1/2 the way between 1 and 2. And let's say, we can do some mixed numbers. How about 3.5? All right, you go out to 3, then go halfway between 3 and 4. That would be 3.5. We could put decimals on there. Let's say we did the decimal for 1/4 would be right over there, about 1/4 the way between 0 and 1. In decimal form, that would be 0.25 or 0.25. Okay. Now, we've already come across a number which is an unusual number. It's given the title irrational. These numbers that you see here are called rational numbers. They're made up of what's called whole numbers. And the whole numbers are 0, 1, 2, 3, sometimes called counting numbers. And then we also have what's called fractions. We've pictured them on there also. And these are things like 1/2, 3/4. Now, technically speaking, we can have improper fractions also. And improper fractions are just another way to write mixed numbers. So you can think of that 3.5 as being a fraction because you convert it to improper. 2 times 3 is 6, and 1 is 7/2, and so forth. Okay. Actually, these two groups together, they fall into the same category. They're known as rational. Rational numbers simply are numbers that can be expressed as a ratio, numerator over denominator. And even these up here, like 3, for example, could be expressed as a ratio of 3 over 1. So therefore, all of these numbers, the counting numbers, the fractions, the mixed numbers, rational numbers. Now, decimals, do they fall into the idea of rationals? Decimals can represent rational numbers under certain conditions, but some numbers have not represented that way. For example, whole numbers have a decimal form, very simple decimal form. If you have the number 1 in decimal form, that's 1. It doesn't change anything. 25 is still 25 in decimal form. In other words, decimals don't alter the whole number notation. They honor it, so to speak. But when you start talking about fractions, some decimals can be written easily as fractions. We looked at this as part of our course. For example, 3/4. If you want that as a decimal, all you do is multiply down here by 25 and up here by 25. And you get an equivalent fraction, 75 hundredths. That's easy to write as a decimal, 0.75. 75, and that's in the hundredth position, so this is 75 hundredths. So some decimals, yes, fractions are really easy to represent. This is called a terminating decimal because it stops. And all terminating decimals are fractions. We also found fractions like this that we spend some time with. Unfortunately, these repeat. These are repeaters. So there's stuff like this going on. In decimal form, 0.333 and so forth. We learned that we can chop them off anywhere we have to, calculate with them and so forth. These repeaters are repeating decimals. Let's put it that way. So it's written the same way. Repeating decimals, again, are always fractions. But there are some numbers which neither repeat nor end, and those are called irrational. So non-repeaters non-terminating those are known as irrational. In other words, they're not ratios. They can't be written as ratios of numerators over denominators. And we've played a lot with one recently, it's pi. No? It has a decimal expansion all right, but it never repeats and it never ends. And that's what's strange about it. And that's the idea that got everyone very upset, 2,500 years ago. There's others. When you go into some of the, you're taking Algebra 2, you'll learn about one called E, which is the base of natural logarithms, and none of that makes any sense to you right now, but that's also an irrational number. And there's plenty of others. There's a whole list of them. As a matter of fact, there's an infinite number of irrational numbers. Yeah. So, if we wanted to picture those, could we? Well, we could do it, but sort of like, just eyeing it in. For example, pi. 3.14159 ... Okay, certainly the accuracy I can get by using this thing on a whiteboard is ridiculously low. So 3.14, okay, that 1 is in the 10th position, so it's about 3 and 1/10, and a little bit more than that, but this thing is so wide, it's ridiculous. I'd have to go 1/10 of the way between 3 and 4. Well, that's a guess, maybe there. But the dot I just put there is probably bigger than 1/10, so I mean, it's kind of a waste of time. But that is perhaps where pi would go. Something like that. You just guess where it is. That's what it amounts to. All right, if you combine these things, which are called irrationals, with these things, which are called rationals, you have all the numbers that fit the entire line. Yeah, you do. Even though that's kind of hard to prove, it's true. There are no other kinds of numbers. Every dot is covered by one or the other, rational or irrational. And this is an infinite line. Therefore, you have an infinite number of counting numbers. You have an infinite number of fractions. You have an infinite number of irrationals. As a matter of fact, between 0 and 1, you have an infinite number of fractions. Yeah, I mean, you know, that's supposed to stop your mind on like Zen meditation, right? You're all meditating, except for those of you that are texting. Okay. It's obvious, I mean, I know you're not looking at your book, so here we go. All right, so that's where the number line is. Now, how about that other side over there? Well, I've never drawn it with that side there before. Well, that's because we have to examine that now. We have to go back to negative numbers. Negative numbers have a place. Anyone play golf? You want a negative score, right?
Oh, yeah.
Yeah, that would be very nice, right? End up with a negative golf score. How about negative temperatures? Unfortunately, those exist also. I found some up in January in Denver. And, oh, I know, how about a negative bank balance? Anyone know about that? Yeah. Oh, come on, you're all lying. So negative numbers do exist. Where we're going to put them, we're going to put them to the left of 0. Now, listen to this, please. To the right of 0, the scale is always constant on what we call the real number line, this one. In other words, this distance between 0 and 1 is the same as the distance between 1 and 2, and so forth. You don't change the scale. All right. We're going to do the same thing back here, but we're going to arrange it in a different way. And to begin with, you might think it's not too intuitive, but it actually works very well. Where am I going to put the -1? I'm going to put it this side of 0, -1, and I'm going to keep the same scale as I have over here. In other words, I don't change the distances between these integers. Likewise, -2 will be over here, and so forth. Now, can we put negative fractions on? Sure. So let's say -3/2 would be -1.5. It would be back here somewhere, -3/2. By the way, 1.5 is a lot easier to draw than 3/2 is. Strangely enough, this is the only real use I can think of for mixed numbers. It's easier to put them on the number line. Can you have negative irrationals? Yeah, -π would be back over here somewhere. So you can fill this in just as much as you fill that in. But notice we have a kind of mirror reflection going on. You know, if you put a mirror right here, this side is being reflected over here, except that you have negative signs on the numbers over here. Otherwise, it is a mirror reflection back and forth. And that develops the entire real line, the negative and the positive. Now our goal here in the next few sections is going to be, well, how do you operate with the negative numbers? And I'm sure all of you remember negative numbers. Maybe it's not a fond memory, but we have to be able to operate with them very well. In other words, if I put up something like this, 1 minus a -2, I don't want 15 different answers. You know, there's got to be one answer, so we have to understand how to do that. All right, let's start doing that kind of thing. We're going to do some definitions to begin with, as you might think. Talk about negative numbers and some ideas that are very useful. Okay, first thing we're going to talk about is ordering. Now we've done this on the positive side of 0, but now we're going to talk about ordering on the entire real line, negative and positive. So if you have something like this, A is less than B, and that's what that sign means, that's how you read it in English. A is less than B. It means A lies to the left of B. And that's all it means. It's a left-right idea. Now, that's not so bad when you're on the positive side. It makes some sense. For example, you could say, all right, 5 is less than 7. Yeah, okay. You know, that's intuitive. But how about something like -3 and -5?
-5 is less.
You have to think, don't you? Yeah. Where's the -5? All the -5's over here, and the -3's over there. Which one's to the left? -5 is to the left. So, actually, if you wanted to indicate this, you would say that the smaller one actually is the -5. -3 is greater than -5. The reason why that stops the mind for just a second is because, of course, 5 is greater than 3, but -3 lies to the right of -5, so it's greater than -5. So that's what you're going to run into with that negative side. You have to be careful with ordering and things like that. So it's strictly a left-right situation. -3 is to the right of -5, therefore it's greater. That's all. Okay, that's the ordering process, using less than and greater than. Second thing we're going to look at is absolute value. Now, we didn't have to do this when we were on the right side of 0, because everything's positive on the right side of 0. So, no problems. We could calculate distances and so forth, and use subtraction. No problem. It's easy on the right side of 0. Absolute value is a mathematical way of saying that I want the size of something. I'm not interested in the sign of it, I just want the size of it. Okay? Size of a number. Actually, officially, it's defined in this way. The distance of the number from 0. So, the notation for absolute value is 2 vertical bars with a number inside. So if you talk about, let's say, the absolute value of 3, all you're saying is, what's the distance of that number 3 from 0? Well, on the picture here, it would be this. 1, 2, 3. Ah, okay. The point being, the distance is always positive. So the absolute value of 3 is 3, a positive number. The distance between here and San Francisco, 110 miles. The difference between San Francisco and here, 110 miles. Distance is always positive. You don't have negative distances, right? Okay? So if I ask, what's the absolute value of -5? I want to know the distance between -5 and 0. 5. So in effect, what happens with absolute value bars is you strip off the signs. If it's got a negative sign, gone. If it doesn't have a negative sign, then you just take the number itself. And that's the absolute value. Okay, third concept on the real number line is that of opposites. Two numbers are opposites. If they are the same distance from 0, but on opposite sides of 0. So if we're talking about, let's say, -3 and 3, the absolute value of that we just found out is 3, and the absolute value of that is 3. They're the same distance from 0. But because of that negative sign, that's on the left of 0, and that's on the right of 0. So this is called a pair of opposites. So it's the number that's the mirror reflection on the other side. That's another way to say it. So if I start out, let's say, a -6 over here, and I want the opposite from -6, I have to go back over here the same distance away. There it is, +6. So we say it both ways. We say -3 is the opposite of 3. And likewise, 3 is the opposite of -3. One's the opposite of the other. Okay, so let's mix this up a little bit. suppose we start talking about things like, I'm going to use parentheses now. This is a notational situation. Suppose I start with the number -2, which would be over there to the left of 0, 2 away from 0, and I want the opposite of it. Well, it's simply unheard of to have two signs next to each other with nothing in between. In mathematics, they will kick you out of the party if you do that. So you put parentheses around it. So that calms everybody down. We're now talking about the opposite of a -2. Well, that would be the number on the opposite side of 0, same distance away, that's 2. Which gives rise to all sorts of little things that students like to remember, like minus a minus, plus a plus, and all that. It doesn't really come from that, but a lot of students remember it that way. Okay, how about this? Suppose we have something like this. Yes, silence. It's exactly what happened. And the reason is you have to think about it carefully. Okay? There are two things here. There are two new notations for you going on here. One is the absolute value bars, and the other one is the opposite sign. Okay? All right. So we do them one at a time. And what you do is you can't really decide on what this is until you know what the absolute value of 2 is. So you go to the absolute value first, and you say, well, that is actually a 2. So now I want the opposite of 2. Well, I know that's a -2. So this thing evaluates to a -2. Suppose you do this. Okay, the absolute value of a -2 is
1.
2. The opposite of 2 is -2. Now, yeah, you do have to think about it. On the other hand, suppose I did something like this. Instead of taking the opposite of the absolute value of -2, suppose I took the opposite of -2. Well, by the definition, you know where -2 is. It's over there to the left of 0. The opposite of -2 has to be 2. Over here on the right of 0. So minus with parentheses around a negative number gets you a positive number. But minus with absolute values around a negative number gets you a negative number. Meaning that the notation is very important. You've got to be careful with your notation. And you actually have to translate it each time, because this is not the kind of stuff we usually think about, you know. So when it occurs on the test, you have to say, wait a minute, I got to slow down. That means something specific, you know, and remember what it means. So this notational problem that you see right here is just characteristic of this absolute value stuff. All right, let us do some homework on this section. An introductory section, and we'll go more into it tomorrow. But this starts the whole idea of the real line. This is 10.1. Time flies, huh? 10 chapters. Where did it all go?
Does that symbol show up in Finland?
Say again?
Does that symbol show up in Finland, or is that like a replacement?